Welcome everyone to the final session of the current edition of CloudWeek. To close off, we will discuss a very interesting topic with our friends at AMD regarding AMD-powered confidential computing. To discuss this, we have a very special guest with us. Welcome, Rob Kypriotakis from AMD. Rob jumped in last minute for Jean-Claude, who unfortunately got ill and whom we wish all the best and quick recovery. Rob has been working in the semiconductor industry for over 25 years. He's currently employed by AMD as service solution architect looking after mega data center customers in EMEA. He has a strong skill set in data networking and data warehousing. Before we kick things off, I'd like to do a little bit of housekeeping. The session that you are about to take part in will be recorded, and we will make the recording available through our typical channels after the event. If you have any questions during the talk, feel free to use the chat features we have in our event app. And we will have time allotted at the end of the presentation for a quick Q&A. And now, without further ado, the floor is yours, Rob. So,
thank you very much. Albert, can I ask you to monitor the chat window because I won't be seeing it when I'm presenting?
Yeah, sure, no problem. I will be doing that.
So my screen should be coming up momentarily.
Yeah, there it is.
There it is? Yeah, okay, great. So, hello, thanks for the great introduction. Like Albert already said, my name is Rob Kypriotakis. I'm a cloud solution architect working at AMD. I work primarily in the server space, and I work with the mega data centers, so think like the AWSs, the Azures, and the Googles of this world. Today I'm going to talk a little bit different of what you probably are used to from AMD, hearing all about CPU roadmaps and great new shiny products. I'm going to focus a little bit more about security and the history of security and some of the new security features that we have available in our platform now and are just now being used and starting to get used, and something you probably want to tell your customers of as well. And who knows, you can also probably use it maybe yourself to increase security footprint in the cloud as well. So with that, let's get started. So for those of you who don't know AMD, AMD has been a company that's been around quite a while. Actually, it's 1 year younger or older actually than our competition. So we started 1 year later with CPUs. You all know probably Intel, AMD has been there just as long. But having been there, we haven't been strangers to kind of innovating in that space. So if you think about it, way back in the 2000s, AMD was the first to break the 1 gigahertz clock frequency barrier. We're also one of the first players to introduce 64-bit extensions to the x86 CPU. We're first to do things like dual core. We have a long history of firsts, and actually in 2017, AMD rejoined the server market with a very innovative new CPU architecture. And actually today, just recently, actually November 10th, we launched our 4th generation of that new CPU architecture. And we're making a large headwinds with that because of the fact that we have a different architecture, a more scalable, more cost-effective architecture, and a more performant in that sense. And everyone buying new servers is more or less now looking at AMD versus Intel because of the fact that we have so high performance and such great energy efficiency that it's a waste of your money if you don't buy an AMD system in that sense. So, like I said already, we have right now the world's highest performance x86 server. These basically are fully compliant with the x86 instruction sets, given the fact that we have a cross license there. So both Intel and AMD share the same instruction set. But we do have the right to innovate in that space, and that's something that we're doing as well. So where do you find AMD CPUs nowadays? You find them everywhere. So if you look at it at Exascale, just recently there has been a supercomputing conference in the United States. and we're now in over 101 of the top 500 supercomputers. Even the number one, actually, we are the highest performance supercomputing, and we're also the most energy efficient supercomputing computer out there. So that kind of gives you a proof point as to how serious AMD and performance is in that sense. Also, the cloud hosters, we have now across the world about 400 different instances of different cloud providers that you can spin up today if you want to, and use AMD technology in the cloud there as well. Also, a lot of our services are being used as backend. For instance, Amazon's S3 storage service, for instance, runs on top of our AMD technology as well. Also, because of the fact that it has lots of I/O capabilities and lots of performance. Also, enterprise IT, that's something that you see now catching up. We do support a lot of different workloads, anything that requires large memory footprints or lots of cores. That's typically where we shine in that space. But enough about AMD and where AMD CPUs fit in there. Let's talk a little bit about security. Like I said, so in 2017, AMD decided to re-enter the server market with a complete new revolutionary server design based on chiplets. But the fact that we are doing a new design also allowed us to do some great innovations in the fact that security-wise. And that's the security features we're going to talk about today is something we have a kind of a marketing term for. It's called Infinity Card. So anytime you hear anywhere you want to serve with Infinity Card or Infinity Card, these are the features that we're talking about here. So let me go into detail. But before we go into detail on what exactly Infinity Card is, let's go a little bit back in time to the days of the 386 CPU and talk about security at the time. Security in the 386 days was extremely basic, to say it mildly. In essence, at 386, we decided, and Intel decided then at the time that we needed something for security, and we came up with this kind of a ring construction. So you have a ring 0 where you have your kernel running, you have a ring 1 where your device drivers run, you have ring 2 where other device drivers that rely on the first one run, and then you have a third ring where your applications runs. And there is policy set in place that, for instance, from ring 3, you can't access the kernel directly. And those were the basic security measures. Think about it. At the time, it was very advanced because we're talking here 1980s or something like that. At the time, we were having way different security problems than we're having today. So, but over time, this model grew, and we soon found that these rings of security, weren't really enough in the x86 architecture. But you saw that at the around year 2000, things like hypervisors started making their entry. Some changes were needed.
Sorry, Rob, I think your microphone cut off. I don't know.
Am I back again?
Yes,
Yeah,
you
okay.
are.
So the solution at introduction of the hypervisor was to invent a ring below the kernel ring, so below ring 0, and we call that ring -1. And then later, Intel started innovating and thought, okay, well, maybe we need additional rings. And they invented rings like -2 and -3 for the system management and the management engine. Well, it kind of became a worldwide ring for all sorts of rings. So any type of new feature was introduced, a new ring was required. And less and less of the security policies were taking into account. And you've probably seen that just a few years ago, there was a lot of talk about security and the ring failures in the space where the management engine would be able to bypass hypervisors, and via the management engines, you could read things like application data and so on. It turned out to be a big mess. So in short, this ring thing wasn't really a great thing. And if you look at it, it makes a lot of sense because let's face it, the world's changed quite a lot when we introduced hypervisors. If you look at the hypervisors and what we call the trusted execution environment is typically right now, if you look at a server, you have your hardware, you have a hypervisor on top of that. And initially you want to isolate an application, an OS, a virtual machine, and part of the hypervisor and part of the hardware dedicated for your environment. So that's really what we call your trusted compute block is. Before that, in the 386 days, we had one copy of one program, maybe with a driver running, and that was it. But the introduction of hypervisors really changed the need for the security model. So in essence, it means that we needed to change that. So a lot of innovation and thought went into it. And if you look at it, this is actually a document of a separate presentation that was done independently of AMD. So this is really what you're seeing here is really a fair comparison in a sense compared to what Intel features, what were thought of, and the AMD features. What we thought of is saying, okay, well, advanced hardware-assisted security mechanisms were required. And of course, hardware encryption and things is a lot faster than doing it in software. And it was true now, and it is now to then at the time, because hardware encryption is way faster anyway. So two extensions to the x86 instruction set were proposed. Intel came up with something called the software guard extensions, and AMD came up with a technology we called AMD memory encryption technology. It's all great technology, more or less designed to address the same thing, but slightly in a different way. So before we dive into our solution and what we did with AMD, let's look at briefly at what Intel did in its time and space. Intel came up with something called the software card extensions. And what it is, it's basically you have an application, and within that application, you have the way to kind of set up what we call a security enclave. You execute some code that is secure and encrypted, and then you come back to your regular application and use the results from the enclave, and then you execute your code. And basically, then the app executes as normal. The downside of using this method is that, of course, your app needs to be fully aware. This app needs to be aware that there is needs for security. And let's face it, if you know on day one where there will be a security breach in your application, you probably would have designed it differently. It's very nice, but this is not really a good scalable way. You really want to keep your app as untouched as possible and still use it in a secure environment. So that's what AMD thought of in that time. What we did is we introduced something called secure memory encryption. And the secure memory encryption is initially actually something we thought of for people stealing memory DIMMs. If you have a memory DIMM, for instance, and you take it out of a system, a lot of people think that, okay, I take it out of the system, all the contents of a memory DIMM is gone. But typically, what you see nowadays with memory modules on a server is that there's an automatic refresh engine directly on the DIMM itself that continuously refreshes. And there's also some capacitors on there to basically power the entire memory refresh algorithm. And if you typically take a DIMM out, within 90 minutes, you can still read the content of the DIMM, although it has been removed off the system. So 90 minutes to take out the DIMM of a system and put it in another system, or even maybe freezing it or having a kind of compressed air to even have it last longer. It's more than enough time to steal a DIMM and put it in another computer and read the contents and maybe discover some passwords or some hidden secrets. So to prevent that kind of mechanism, we came up with something called a memory encryption engine directly in the DRAM controller. So every write that happens to memory can be fully encrypted. And that's something we call secure memory encryption. That's something that's been around for quite a while, and in essence, we developed this for notebooks. When notebooks were in sleep state, that even the entire memory would be encrypted even while it was in sleep state. With the introduction of server processors, we kind of took that technology and extended it to the higher end server CPUs, and we actually also added the capability of, instead of having just one key, to be able to use multiple keys. So you can have a different key for each and every VM container, you name it. Depending on what policy you set, you can have a different encryption key. So you use the same security encryption, but every enclave has their own key. The nice thing is it's encrypting all of the memory. That means that there's no need for any change in the application or your VM or your code or whatsoever. So you can use security. The only thing that needs to be aware of the security feature there is your OS or your hypervisor in that sense. So the hypervisor needs to be aware to initialize the security and set it up and keep it up and running. So that's the solution AMD thought of. So we all brought it together, and now we have the great marketing term called an AMD Infinity Card, which I touched about earlier. But what is AMD Infinity Card? If you look at AMD Infinity Card, it has several components. First of all, there's a security processor. That means that in every single chiplet, every COC, every socket of AMD you basically buy, there's a security processor within that same chip. It's a separate processor from any kind of the regular processing core, so it functions completely independent. In fact, it's a completely different core. Strange as it may seem, it's based on an ARM core. So actually, if you think about it, we're running an ARM core directly within an x86 core. They're completely separate from each other, so they can't execute each other's code, or they can't even get into each other's memory space. It's just there to basically set up the memory encryption and the memory keys for the memory encryption in the DRAM controllers. So it does full encryption. Right now, it's the CPUs that are currently on the market support AES 128, and with the new edition of the 9000 series of CPUs we just launched last week, actually, we now support also AES 256 encryption for the memory. The other thing it does is also allows you to set a secure encrypted virtualization environment where even things like your registers are completely unique. So even if you switch from one VM to another, you can't really dive into the CPU and see what the previous content of registers was. So that's also fully uniquely encrypted. The other thing that's a feature that's primarily interesting for Microsoft players there is we have support for AMD Shadow Stack. And AMD Shadow Stack is something that has to do with return buffers, where if you jump to another location and if you modify some code there, so you have code that modifies the main application code, you could mess with return parameters and as such execute another part of the code which you didn't intend to execute. So AMD Shadow Stack has been designed to kind of prevent these stack overflow errors. So what is the security processor? Like I said, it sits within the SoC. It runs its own kernel. It's a dedicated kernel. It basically has it's its own boot ROM. It sits directly on the chip, so it's not something you can modify the boot ROM. As soon as you start tampering with it or accessing it, you basically invalidate it and it won't run anymore. So it's directly contained within the chip. It does it. It provides the key generation, and it's all been certified, so that's been tested and so on. It's proven key generator there, and the only thing the key generates the key for the DRAM protection. So it's not like if you use OpenSSL traffic that you use the security processor to do that. The security processor is just there to generate keys for the memory encryption. The other thing it does, it's basically make sure that the processor boots, and actually the entire system boots in a secure way. And that's what is done with what we call something called secure validated boot. And that's something that hasn't been new. It's been around for quite a while, but the way we're doing it, we don't do it with an independent, what's called a trusted platform module. We have this security processor directly in the chip. What it does, it boots its on-chip firmware. Then it basically does the off-chip firmware. It loads the bootloader. It checks and authenticates the BIOS, and if the BIOS is authentic, it will execute the BIOS, and then it starts loading things like the UEFI firmware and does the OS boot also in a secure way. So actually, from the power on moment till the OS running, you have a fully secure and validated system that you can guarantee that you know what firmware is running and you know it comes from a trusted source. So that's the one thing the security processor does. The other thing what it does is the memory encryption. Here you kind of see a kind of high-level diagram of where it works, how it sits. And if you're starting a VM, for instance, the EPIC processor sees as it wants to initialize a neural virtual machine environment. It talks to the security processor. The security processor will generate either a new key, or if it's the same VM that's already been running, it will use the old key. But if it's a new VM initialization, it will generate a new key and set it up in the memory controller. The memory keys that are supported, you see the table to the right. We have anywhere in the first generation, we had only support for up to 16 keys. The current generation is up to 509, and the recently released CPU, we now support more than 1,000 encryption keys. So that's our individual keys for each and every individual VM or container, or however you want to separate it. So the encryption key works by the virtual machine ID. So you have a different virtual machine ID, a different key gets used. That's in short how that works. The shadow stack, I already briefly talked about it. That's also a feature of the security processor, and it's what we call stack protection in case of stack overflows. So let's go a little bit further into the difference, what feature is available where. So again, the memory encryption, that's really been around and has been all over the place since the first generation of our AMD CPUs. The secure encrypted virtualization has been there. The register encryption has been there also from day one. Something that's new is the secure nested paging, and what that is, I go into a little bit more detail later on. That's only been available recently since the Zen 3 introduction, so that's been on the market now for about a year. And the rest of the features are then available. But let's talk about the memory encryption and the memory controllers. So we already talked about individual controllers and the security processors setting up that environment. Typically, what you see is that a VM or an application runs in clear text. Security really it's really ends at when the data enters the system. You have all kinds of great things like disk encryption, network encryption, and so on. But most systems that are out there right now only run an application in clear text. That's all great and well, but what if you don't trust your cloud provider, or if you don't know, your competition might be running on the same hardware? So first of all, we put mechanism in place to prevent a third party from accessing your memory. So you say, okay, we set up an exit validation or page invalidation if VM1 starts to talk or mess with VM's memory space, for instance. That's all great and well, but you can still get to the data. So if there's a faulty hypervisor or there's a bug in the hypervisor, theoretically one VM could read the contents of another VM. So to prevent this thing from happening is we have these encryption keys. So the encryption keys means that even if with all the security measures that are put in place, you are able to read from the VM's different, one VM1 can read from VM2, if that would be possible, then it would still be reading a completely garbage because it's fully encrypted content. That's all great and well. So you kind of get the security by encryption enclave. But also, what about the hypervisor? Let's face it, a lot of people are kind of prone to, if you run a workload in the cloud, do I trust this hypervisor, or do I trust the administrator running the hypervisor? There have been cases, for instance, with AWS. There has been a bank in the US that has been frauded by an administrator of AWS that was able to steal credit cards because of the fact that he had admin access to the hypervisor. So yeah, okay, you try to prevent that, and basically the administrator got fired, but still, the theft happened. So there was a possibility to do that. So that's why we set up a system to not only have an encryption key for the VM, but also, if you look at it, the system, the firmware that it runs, has its own encryption key. The hypervisor has its own encryption key, and then the VMs have their own encryption key. So even a VM, if you control as an administrator, if you control the hypervisor, you can't access the VM memory. All you see is basically garbage encrypted memory. The other way around as well, a VM can't see in the memory space of the hypervisor. They're all separate enclaves. That's how this entire system has been designed. So what's the sequence? Kind of like I said, the system asks the security processor to set up a key. That happens in the memory controller. The security processor mentions via the secure API to the hypervisor that the page has been set up, the memory controller has been initialized, and then the guest OS can run. And the nice thing, if you compare it to what we had with SGX, where you needed to modify the software, in this case you have 0 modifications that are required to anything in the VM. So either your application or the guest OS, they don't need to be aware of this virtualization, of this encryption happening. The only time where you need it is when you want to do things like secure injection. So if you want to inject keys, for instance, or you want to securely inject a certain program image, that's where you need to be aware that the guest OS needs to be able to talk to the security API that we put in place. The security API is part of public record, so on the AMD website you can find complete detail on that API and all the different calls you can make and from where you can make that call. So it's been under scrutiny for quite some time already, and so far we haven't been aware of any security breaches in that space. So the different technologies. Well, we talked about the secure encrypted virtualization and encryption of register states. That's been around for quite a while. So any kind of Linux kernel that's out there, anything older than 4.15 has support for it. But also things like the hypervisors from Microsoft, so the Hyper-V, but also VMware, for instance, is also fully supporting these features. But the one thing that's new, and that's something that was actually launched last year with the third generation of AMD EPYC CPUs, is the secure nested paging, the SAV SNMP. And what it does, it allows you to set up, keep a list of pointers as to which VM is supposed to access what area and which VM is it. And why that came about is precisely the topic I talked about earlier. So if you look at the threat model, what do you know? And if you think about it, you see to the right, you see a model of the AMD hardware and the firmware. That's something we can, with secure boot at least, you can trust that the hardware is secure, is integer, no one has modified it. The firmware running on that hardware has been integer, has been running. And the only thing you can guarantee is the secure encrypted image that you made of your virtual machine. Those are the only things that you can really trust and you have your own control over. But if you think about it, if you go to a cloud provider, first of all, do you know the CPU? Do you know the BIOS that's running in there? Do you know the device drivers that are in the system? Do you know the hypervisors, the management software, and all the other VMs that are running on that same hardware that you're sharing? There's no real trust in there. And if you think about it, there's also, well, you can trust someone on this blue eye saying it is secure, but it really, there's no mechanism of proving and using it. And that's actually what we try to tackle with SNMP, where you said, okay, let's make an environment where all these red components aren't trusted. We don't know. We think they're secure, but we can't guarantee it. What do we need in the hardware to be able to support it and be able to run in this kind of a secure environment? So what we did there is that we came up with secure nested paging. And what secure nested paging is very simply illustrated here. So kind of the same thing. We have this encryption area here, and we have the VMs. But every time a VM accesses memory or wants to access memory, there's what we call a reverse map table, the RMP. What happens there is it's a page table. So every 4K block, there's an entry for each and every VM, and it checks there if it's allowed to write and if it's allowed to read in a certain memory space. So if there is a validation, so if one VM or if an hypervisor tries to read in a page to which is not authorized, it will generate a page fault as this area, and the hypervisor will basically take measures there. So it will either kill the VM, hold the VM, or it will shut down completely, depending on the security policy you check. So there's a way now to see and check and verify the integrity if your VM is running, if it's accessing the correct content, and if these contents have been breached or not. So that's what we do with the RMP table. This RMP table is something that's completely dynamic. It's generated at boot time, and it's filled up as VMs get created and get killed. So some examples, like I said, it contains per 4K of memory. There's one entry in the RMP table. This basically means there's entries flagged for firmware, there's entry flagged for the hypervisor, for the virtual machines, and they're all mixed into each other. So the only thing, when there is a validation, so when guest 2 tries to access guest 1 page, for instance, that's when an error gets triggered. And this is something that is not modifiable. This is something that happens in the hardware. So it's not something that the OS or the hypervisor controls. This is purely monitoring in the hardware. And whenever a failure or a validation error happens, then basically an interrupt gets sent back to the processor. It sends out what we call a page fault. And the OS and the hypervisor can take action according to that page fault. So that allows you to even not only have the guests isolated from each other, but also the hypervisor. So the hypervisor can also run into a secure enclave. So this is a lot of the technology, but I can take, okay, what is all this technology? What is it securing? What does it bring to the table? Well, here you see a list of kind of security features that we are potentially preventing with these features. So things like confidentiality. So is my VM memory, is it really the VM memory that I wrote before? So it has the contents be modified. But also the state of the registers, have these been modified when I do a content swap? but also things like DMA memory. So when I have network transfers, if you have very high-speed networking in a virtual machine, then what typically happens, you have a DMA transfer directly from the network card into the virtual machine space. So that's also something that needs to be secured. Also things like integrity protection, and that's something, most recently people starting to be aware of that it is an issue. Things like replay protection. For instance, think about you do a database query. What if you take a previous executing database query and you replace it again in VM memory to be re-executed? You can really do some creative things there, mess up databases, or get content out of there that you're not supposed to access. But also maybe kind of do an denial of service attack on a VM. So once you know that your competitor is running on the same hardware, you can also say, well, if I fill the VM memory with junk data, and I can shut down the VM because I corrupt its main memory. That's something that until recently was also not thought of. Also, things like memory aliasing. That's something that VMware was very famous for. When you start a VM in VMware, for instance, it's first of all you have your dedicated memory, but then as it figures out that, oh, we're running 2 copies of Windows, for instance, it starts merging the pages together and starts reducing your memory footprint. If you're running in a secure environment, you want to be running your own secure version of the OS. You don't want someone else executing in the same area in that sense, because that will open you up for attacks. So that's also something that's now being able to do. We are now able to do that with secure nested paging. Things like memory remapping, where you basically reorder the memories. That's something as a process that a hypervisor does continuously. It moves memory pages around to make it optimized, to make sure that the memory pages that it's using is sitting close to the core on which it's executing, for instance. That's a process that happens all in the background. But you could also, if you're a creative hacker and you have control over a hypervisor, you could easily say, okay, I want to remap the DRAM to another core, and as such inject other code or monitor the code that's running into that in that environment. So that's also something we prevent with secure nested paging. Availability, denial of service attacks, and that's also something relatively new. So if you have a hypervisor and you don't trust that hypervisor, a malicious hypervisor could basically say, okay, I'm running a VM, but I'm not giving up resources to that VM. So I'm keeping it in a locked state. So you think the VM is running, but at the same time, it doesn't get CPU cycles to execute its code, or it doesn't get access to IO components or to memory. That's also something that we tackle with this memory encryption technology. Things like physical access. Well, I already talked about it, removing DIMMs, and to be honest, it's probably, yeah, you can easily remove DIMMs from a notebook, for instance, or from a desktop CPU system, but from a server that's a little bit harder. But that's also a technology that's, of course, you could theoretically run such an attack on the server as well if you have physical access to that server. But to be honest, that doesn't happen too often in the server space. This is really more of a technology security issue on notebooks and clients in that sense. But that's also still something that's possible. But that's something that we encounter with this secure memory encryption. So in summary, what do we have here? Protecting VMs from malicious hypervisors is something that's relatively new, and it's something that we can now bring to the table. Secure nested paging takes it to a whole new level where you can also modify the integrity and get things like attestation reports. And this is something, if you think about it, you might be aware of it. Right now, for instance, Azure has what they call confidential compute. Google offers also a confidential compute configuration. They all use this technology to make this happen and realize it. And actually, since the introduction of secure nested paging, we have enough of the features there that you can say, okay, we can guarantee the VM is running. We can also give you an integrity report of if they have memory validation, if the memory map has been corrupted, or if it's still secure, it's running in a secure environment. And the nice thing is it runs in a remotely managed hypervisor, and all the Google management and the Azure management happens in the background. But you can guarantee that even the hypervisor or any administrator running or having access to the server hardware can't access your VM. And what we've been seeing is since we introduced this feature, so this is now available for about 2 years, it's on the market, and it's available first in Google, later in Azure, and what we see also AWS will follow shortly as well. Is that this feature is opening up cloud support for a lot of different customers. I used to work at a financial institution, and they were very hesitant in moving to the cloud. And by having these kind of security features now, they're trusting all even their most secure workloads and migrating those to the cloud because they know and they can guarantee that it runs in a secure and encrypted environment. So it kind of opens up, new customers to the cloud, and it lowers the barrier of entry. It's a bit hard to explain and convince customers that these features are available and to make sure that it's guaranteed. And again, if you are in the customer discussion and you want to convince them, you feel free to contact AMD or your AMD partner to help you convince customers. But typically, once we have the discussion with them, and once they see the value and we can talk them through what the API is and how it works, and show them how things like Google or how Azure implemented, a lot of people are convinced that this is the way to go forward with trusted computing. And the nice thing going forward as well is you'll see that also now Intel is still supporting the SGX extensions, but they also see now the technology that we bring to the table. And as of the new generation, they're also supporting this similar kind of memory encryption technology. And that will also be in the CPUs as well. So that's kind of my presentation. With that, I'd like to thank you for your time. I'd like to open it up for any further questions. So let me go back to the chat window to see if there are any questions.
Yeah, I've been monitoring so far. There are no questions, but if anyone has, please ask them. I've got one question regarding what you said right now about clouds implementing this into their offer. What do you need to choose within a cloud to be able to take advantage of this offer? Is this a special kind of machine that is offered, or is this a special additional service? How do the cloud providers implement it?
Well, of course, if we would love to have one single way to implement, but each cloud provider tries to do it differently, and some charge money for it. Others basically say it's a fee charge for you to use.
Mhm.
But typically, if you take, for instance, Google, at the time you create a VM, you need to select the VM type, and that's currently N2D for Google and C2D for Google. And at the time you create your VM, there's one checkbox item saying, do you want to run this in a confidential mode or not? And once you click that, it basically automatically configures it for encryption and encryption support. That's it in that sense. Azure, it's a little bit different. You need to select a specific instance, and they call it confidential compute instance. And once you have that instance, then you're basically running in a secure environment.
Okay, thank you. Do you know anything about AWS in this regard? Is this also a special type of machine?
I know, but unfortunately, since I haven't released it yet, I can't give you a lot of more details on that.
Okay,
that's really for AWS to figure out and how to make money out of it. They're very creative in that sense.
Okay,
but until they release it, I can't go into details on that. But they will support it.
Okay, I understand. Thank you very much. Okay, I don't really see any other questions or anyone asking questions. So, yeah, I think that we can leave it at that.
Great.
So again, thank you very much, Rob, for this talk. It was very informative, and it's good to know that these features are available. And if they proliferate throughout the clouds, it's even better because we do have some customers who may really be able to take advantage of it right now.
Absolutely, and keep in mind that this is not only for cloud. So even if you have physical hardware out there, if you're running your own VMware, you're running your containers, or you're running a Linux KVM environment, you can still make use of this as well. So it's not only for cloud service providers in a sense. It's definitely, if you have an Epic CPU, you can use its feature.
Definitely. Okay.
Thank you for the opportunity to present. And if there are any further questions, feel free to contact us.
Okay, great.
Sure.
Yeah. So everyone, thank you very much for your attendance, and I hope to see you again in the next editions of the CloudWeek. So thank you very much. Bye-bye.
Bye-bye.